When we instantiate a deep neural network's regressor, we specify a value for the hidden underscore units argument. What does this argument specify and how does it affect the structure of our neural network? Now that we've explored the data split into training, test, and prediction datasets, we are now ready to set up our feature column types for our DNN regressor estimator. For this, we need to understand the various values that are contained within the columns. Our exploration still continues. These are the various makes of cars that are available within our dataset. We'll explore those columns that have categorical values first. If you remember, categorical values are discrete values or labels which are present in our input data. Fuel type, aspiration, number of doors are also categorical values. Fuel type can be gas or diesel, aspiration can be standard or turbo, and number of doors can be 4 or 2. Even though number of doors seems to be numeric because there are only two types, that is a categorical column. Explore the other categorical columns as well, that is body style, drive wheels, engine type, number of cylinders, and fuel system. We'll now set up the feature columns for our estimator. The DNN regressor is essentially an estimator, the high level scikit-learn like function that we studied earlier when we looked at regression models. This makes building and training machine learning models in TensorFlow very, very simple. These are the numeric columns which serve as the input feature vectors into our DNN regressor: curb weight, engine size, horsepower, rotations per minute, miles per gallon in the city, as well as the highway. Notice the TensorFlow library tf.featureColumn.numeric column that we use to set up these column types. We use a different TensorFlow library to set up the categorical columns that we saw earlier. The categorical column type for body style we set up using tf.featureColumn.categorical column with vocabulary list. Categorical column with vocabulary list basically indicates that we know what discrete values this categorical column is going to have. We know the vocabulary for the values of this column. The key to this column is body style, which is the name of the column, and the vocabulary list is basically the unique values in this column. Set up the categorical columns for all the other columns that we explored just a little while ago: fuel type, aspiration, number of doors, and so on. You can use a different TensorFlow library function to set up the column for a categorical value if you don't know the exhaustive list of what values that column might take. This is the tf.featureColumn.categorical column with hash bucket. This simply hashes the values that are available in that column. Our bucket size here is 50. This is the library function that you'll use from TensorFlow if you do not have an exhaustive list of what values could occur in this column, and it's a categorical column. So this categorical column with hash bucket represents sparse features where the ID values of those columns are hashed. Let's collect all these column specifications together into one array in order to feed it into our DNN regressor estimator. First up is all the numeric columns. In a dense neural network, you can't use the categorical columns directly. You need to convert the categorical columns from a sparse representation to a dense representation, and there are two ways by which you can do this. The first is by using the TensorFlow library function, the indicator underscore column. The indicator column is basically a multi-hot representation of a categorical column. So it's not one hot, it's multi-hot. It's not really needed in the case of body style because your car can have just one body style. But suppose two values were allowed for the body style of a car, this multi-hot representation would be able to capture both of these values. Or another thing that you could use is the tf.featureColumn.embedding column library function. This is used to convert sparse categorical representations into a dense format called embeddings. And these embeddings are extremely useful and very often used when you want to use dense neural networks. Depending on the range of values for your categorical column, you specify the number of dimensions for your embedding. Here it's just 3 because each of these categorical columns don't have too many values within it. I'm using the embedding column here to represent the remaining categorical columns, all except one. All of these columns have between 2 and 5 categorical values, which is why dimension is equal to 3 suffices for them, except for make. Here I'm using larger number of dimensions because the make of a car can take on about 9 different values. Let's set up the input function that we'll use with our deep neural network estimator. If you remember, the input function is our bridge between the features of our data set, the corresponding labels, and the actual machine learning model. The arguments to this input function method is the x data, the y data, the number of epochs for which we want to run training, and whether we want the data shuffled or not. Now, the cool thing about using a pandas data frame to represent your data is this built-in function that TensorFlow offers to convert your data into an input function. tf.estimator.inputs.pandas input function takes in a data frame and your y labels and returns a corresponding input function. And the arguments that you pass in is the x data, y data, the size of your batch, the number of epochs, and whether you want the data shuffled. We are now ready to set up our deep neural network regression estimator. Notice how we are going to set up a neural network without specifying any layers at all. All the arguments that the DNN regressor needs is the number of hidden units. The number of hidden units is essentially the number of neurons that you want in each layer of your neural network. The DNN regressor estimator will build this neural network for you internally and carry out training. We initially specified 2 layers within our neural network. Each layer has 20 neurons. To this neural network, we pass in the feature columns that make up our input data. Once you've instantiated the model, you can run training by simply calling model.train. There is no session that you need to set up. The input function will pass in the features and the labels for training this data set. We specify the input function, and the data that you pass in is the training data, x train, y train. We set num epochs to none here. The reason for this is that we've already specified the number of steps for which we want to run the training process. If you specify the number of steps, it's not necessary for you to specify the number of epochs. An iteration through one batch of data is essentially one step. A pass through your entire training data set, however many batches it is divided into, is one epoch. So you can either specify epochs or steps. If you specify steps, you can set num epochs to none. We specify the number of steps. Steps is equal to 10,000. Go ahead and hit Shift Enter so that your model starts training. And this might take a long time. I'm just going to speed up the video so that you don't have to wait around watching it train. Notice the loss for the final step. Our model has been trained. Let's see how good this model is. And you can do this by calling model.evaluate. Model.evaluate takes in the same input function that our model.train did, except that this time we specify the test data in this input function, x test, y test. We set num epochs to 1 because we want to pass through this test data exactly once, and we don't want to shuffle this data. Data is typically shuffled only during the training process. And here are the parameters calculated on our test data. These are the parameters which tells us how good our model is. Now it's hard to understand from these parameters how exactly our model performs. Let's kind of print it out in a more systematic way. The average loss is 1.98 and the loss is 63.38. Once again, doesn't make much sense. Let's extract the average loss and calculate a metric that might make more sense in this regression problem. Because this is a regression problem and the predicted value is a continuous range, this metric is the root mean square error. This is a measure of how far the predicted values are from actual values, the predicted prices from the actual prices of these automobiles. Notice that we multiply this root mean square error by the price scaling factor to get a number in dollars. And this dollar number works out to be around 14,000. Now, this is pretty bad. That means the predicted prices can be on an average $14,000 off from the actual price. Now, you can't be plus or minus $14,000 and really rely on this model. Let's run this model on the prediction data set that we'd set up and actually see how far off the predicted price values are from actual prices. Run the model.predict method with the prediction data set. Num inbox is set to 1 and the data is not shuffled, just like we did with the evaluate, and store the results in predict underscore results. Predict results is an iterator. We use the iter tools to get the result in the form of a list and store it in predictions. Now, if you list out the value of this predictions variable, you'll get a bunch of numbers which don't make any sense. This is because these are the scaled down price predictions. You need to multiply them by the scale factor to get actual price values for the automobiles in our prediction dataset. Extract the scale down predicted prices from the list that we saw earlier and then multiply it by the price scaling factor. We iterate over the objects in the predictions list. Within the object dictionary, predictions is an array and the zeroth element of the array is our scale down price values, which we multiply by the price scaling factor. Here are our predicted prices. Now you know this model isn't very good because we have a negative price in there. We need to do a side-by-side comparison of actual prices versus predicted prices to really see how good or bad this is. Make a copy of your original predictions dataset, that is the compare underscore TF. And to this data frame, add in the actual prices of these automobiles and the predicted prices as well. This will allow us to do a side-by-side comparison. Now, if you list out compare DF and you go over to the actual and predicted prices, you'll see how our model performs. Some of the predictions aren't really very bad, such as the first two examples, and some of them are just terrible, as in the case of our negative price. And the last instance is pretty poor as well. The predicted price is around $25,000. The actual price is around $6,500. Now, this model will obviously improve if we have more training data, but we do not have that luxury. Let's see if we can tweak some of the other hyperparameters to get a better model. We'll start off with how long we train. We increase the number of steps to 20,000. Run training for this model and step through the rest of the code till we evaluate the model. Notice that the loss now is just around 38. With 10,000 steps, the loss was around 63. So clearly this model has improved. Let's see how our price predictions have improved because of this model. Step through the code and we find that the root mean square error is now around 10,900, an improvement from around 14,000 that we had earlier. Continue stepping through the code till we can compare the actual prices with the predicted prices, and you'll find that this time we do a lot better. There are no negative price predictions, that is a huge plus, and the prices are closer to the actual prices, though still far enough away that we won't trust this model. We'll continue training for 20,000 steps, but this time we'll change our neural network architecture. Instead of just 2 layers, we'll set up 3 layers of this dense neural network, 24 neurons in the first layer, 16 in the second, and 24 in the third. Execute the remaining steps and you'll find that the average loss has dropped significantly. In my case, it's come down to 4.64, down from 38. The root mean square error is also much lower than before. It's $3,800, that is $3,800, which means on an average, our predicted price should be no more than around $4,000 away from the actual price. Step through this code and let's compare the actual prices with the predicted values. And you'll find that this time our model looks pretty decent. The little bit of hyperparameter tuning that we did has resulted in a better model, a model with better predictive power. The hidden underscore units argument to our deep neural network specifies the number of layers within our neural network and the number of neurons in each layer. This is specified in the form of an array where the number of elements in the array is equal to the number of layers of the neural network, and the value of each element is the number of neurons in each layer.